In this final session on calculus of trigonometric functions, we're going to revisit a couple of topics that we've looked at before, but this time we're going to look at them in the context of trigonometric functions. So we're going to start off by looking at volumes of revolution, and then we're going to look at linear motion. So we should remember from our work previously that we can find the volume of a 3D shape by using integration. So for instance, if we had this function here, y equals f of x, and we revolved that around the x-axis, it would form this shape here. So it would form this kind of cone shape here. And if we wanted to, we could find the volume by thinking about a slice through the shape. So if we were to take a slice through the shape here, we know that the radius here would be the y value. So if we wanted to find the area of this circle here, it would be pi times the radius, which we're saying is y squared, multiplied by the depth. Now, we're going to use calculus to increase the number of these slices such that they become infinitesimally thin. And at that point, we will be able to find the volume by adding up the area of each of these infinitesimally thin slices. And that will enable us to find the volume using this theory here. So in effect, we've taken, this is our pi y squared, or pi r squared, and we're just going to integrate between our upper and lower boundaries, and that will give us the volume. So we should really be able to take that concept and then apply it to trigonometric functions. So knowing what you have learned about differential calculus of trigonometric functions, just try and have a go at this question by yourself, and then follow through the response. So in the first instance, we've been given this graph, fx equals x sine x, and we're asked to find the area of the shaded region. So before we even look at any volumes of revolution, this is a simple, straightforward integral calculus question. The first thing we're going to have to do then in part A is to establish the x-intercepts, as these will form our boundaries. So in order to do this, we're going to take our function fx equals x sine x, we're going to set that equal to 0 and solve for 0. So the only way this can equal 0 is if x equals 0 or if sine x equals 0. So if sine x equals 0, then x could equal 0 or pi. So we've got our two solutions here, going to be 0 and pi, and we can then take that and use those as our boundaries and integrate our function between these limits to get an answer of 3.14. For part B, we're asked then to find the volume of the shape that would be formed if we rotated the shaded region through 360 degrees. And this then is where we're going to take our formula of pi, the integral of y squared. So y is our function, so take our function and substitute it in here. And again, we can just do this on a calculator, so we don't need to work this out. And if we do that, we get an answer of 13.8. The other concept that we can revisit is finding the area between two curves. And again, this is something that we've seen before, but just not using trigonometric functions. So we should recognize that if we had two functions in which one is greater than the other in a particular domain, then we can find the area between them, by finding the integral of the first or the greater function or subtracting the smaller function. That will give us the area. Just to remind you then, when we're talking about quadrants in a graph, these are the four quadrants. So in this question here, we're asked to find the area of the region in quadrant 1 that is bounded by the curves y equals 0.4x and y equals sine x. So we're just going to be concentrating on this. So have a quick go at this question and then check how you get on. So here, the first thing you're going to do is take your calculator and plot both of these graphs. We can see in this instance that y1, or the larger curve, is sine x, and the smaller curve is 0.4x. So your y1 is sine x, your y2 is 0.4x, and we can use our analyze graph, find the intersect tool to find the intersection here. So we will therefore be integrating between 2.125 and 0. And then we're going to put in sine x minus 0.4x, and on our calculator we should get the answer of 0.623. Linear motion then, again, should be more of a review exercise this. If we have a displacement function, remember we use the letter S to denote displacement. If we differentiate that, the rate of change of displacement is the velocity, and we can differentiate the velocity, i.e. the rate of change of the velocity, to get the acceleration. So acceleration can be written as AT, or the derivative of VT, or the second derivative of the displacement. And also recognizing that the total distance travelled between two time periods can be found using the integral of the modulus of the velocity. And the conventions: if the object is at rest, the velocity is 0. If it's moving up or right, it's greater than 0. And if it's left or down, it would be negative. And the relationship between speed and velocity is that velocity is a vector quantity, so speed is just the scalar part of that quantity, or the size. So speed would just be the modulus of the velocity. So bearing that in mind, you should again be able to draw on your knowledge of differential calculus of trigonometric functions to have a go at this question. So make a start, or if you need to, get started by following through the next few steps. In the first instance then, find the particle's velocity. So we said that velocity is a derivative of the displacement. So we've got a displacement function here. All we need to do now then is just differentiate it. So to differentiate it, we're going to have to use the chain rule. So this is the constant multiple rule as well, because it's -2 multiplied by this. So when we differentiate cos, we're going to get negative sine, so it's going to be negative sine 3t multiplied by the derivative of 3t, which is just 3. So if we expand that all out, that's going to give us 6 sine 3t. The acceleration is going to be therefore the derivative of the velocity. So if we said the velocity is 6 sine 3t, then again we are going to, in the first instance, differentiate the sine to give us cosine 3t, and then multiply by the derivative of this, which is just 3, and multiply by the constant in the front, and that gives us 18 cos 3t. For part B, then find the particle's initial displacement, velocity, and acceleration. So substitute in for 0, and you end up with a displacement of 3, and substitute in for 0 into the velocity, and you end up with a velocity of 0 meters per second. Final acceleration there, again substituting in for 0, gives us 18 meters per second squared. Find when the particle is moving to the right, to the left, and stops in this time interval between 0 and pi. So first of all, you are going to need to take the velocity function, which we found previously, and set that equal to 0. So you'll be solving here to find the stationary points. So sine 3t equals 0. 3t in this interval can be there for either 0, pi, 2 pi, or 3 pi, because t is going to be between 0 and pi, and we've got 3t, so it could be between 0, pi, 2 pi, or 3 pi. Therefore, t, we need to divide each of those by 3. So these are our stationary points where it is at rest. In order then to ascertain where it's moving left or right, a bit like when we're finding maximum, minimal, or points of inflection, we've got our stationary points here, and we're going to test some values either side. So we can see that here it's moving right, here it's moving left, and here it's moving right. The final part, then write down a definite integral that represents the total distance travelled between 0 and pi seconds, and then use the GDC to find that distance. So the integral here, then take our velocity function, take the modulus of that velocity function, integrate it with respect to t between pi and 0, and you end up with an answer of 12 meters. Final question then, a particle moves along a straight line so that its velocity at time t seconds is given by vt equals 5 sine t cos squared t. First of all then, have a go at finding the speed of the particle when t equals 5 pi by 6 seconds. Secondly, when t equals 0, the displacement of the particle is 3 meters, and you need to use that information to find an expression for s in terms of t. And then finally, find the expression for the acceleration a of the particle in terms of t. So for part A then, all we're going to do is take our value of 5 pi by 6 and substitute that into our expression for the velocity function, which means we ideally need to know our exact values in order to work out 5 pi by 6. So that's the same as 150 degrees, which we know because we can reflect the sine values in the first and second quadrant would be the same as sine 30 degrees, which is a half. Cos 5 pi by 6, so cos 5 pi by 6 would have the same size as cos pi by 6, which would be root 3 over 2. However, because it's reflected in the second quadrant, the value would actually be negative. So this should be negative. However, because we square it, it won't matter. We'll still get an answer of 15 over 8. And we are asked to find the speed, not the velocity. So therefore, we just need to be cognizant that we need to take the modulus. So here it won't make any difference, but sometimes it might do. So the speed, therefore, is 15 over 8 meters per second. When t equals 0, the displacement of s is 3 meters. Use that to find the expression for s in terms of t. So in this instance, we know that if we have the velocity function, we need to integrate that in order to get an expression for the displacement. In our function here, we can see that if we set u as cos t, we have du by t equals negative sine t. And up here we can see we've got 5 sine t. So it's not quite the derivative of this, but we can see that we can manipulate it. And we end up with negative du by dt would be sine t. So we can substitute in negative du by dt for sine t, multiplying here by a constant, and here we said that's u squared. So this is the equation that we've got. We can take out the negative 5 as a constant. The dt's will cancel out, and we're left with integrating this, which is going to be the same as negative 5 multiplied by a third, u to the power 3 plus the constant term c. Fortunately, however, we know that when t equals 0, the displacement of the particle is 3, so we can use that to substitute in and solve for c, which yields a value of 14 over 3. So the expression is going to be the displacement is negative 5 over 3 cos cubed t plus 14 over 3. Final part then, find the expression for the acceleration. We know the acceleration is a derivative of the velocity. So if we've got the velocity function here, we're going to have to use the product rule and the chain rule in order to differentiate this, and we will end up with negative 10 sine squared t cos t plus 5 cos cubed t.